Module 1, Lecture B. What is algorithm? By the end of this lecture, you will be able to define an algorithm and distinguish it from a Python implementation, explain the importance of correctness, efficiency, and readability in algorithm design, and classify simple everyday tasks as algorithms and map them to Python-style steps. What is an algorithm? Formal and informal definitions. In computing, an algorithm is more than just code in a particular programming language. It is a clear, finite sequence of unambiguous steps that takes some input and produces an output, and it must always finish in a limited amount of time. This definition treats algorithms as abstract procedures, like precise instructions that any suitable agent could follow. The emphasis is on the logical structure of the steps, not on the specific technology, syntax, or device used to carry them out. Algorithms are clear, step-by-step methods for solving problems or completing tasks. In everyday life, following a recipe, picking a route, or using a bank's loan approval process are all examples of algorithms when they are precise enough for someone else to repeat. This shows that algorithms are structured procedures we use regularly, not just abstract mathematical ideas. Whenever we follow a consistent method instead of improvising, we are effectively using an algorithm. An algorithm is the core logical process for solving a problem, and it is separate from any specific programming language, syntax, or hardware. You can describe an algorithm in plain language with a flowchart or using pseudocode, as long as the sequence of steps stays the same. A Python implementation is just one concrete way to express this logic so a computer can run it. Different programmers may write different Python code that still follows the same underlying algorithm. So it is important to focus on designing clear, solid algorithms before turning them into code. Inputs, outputs, steps. An algorithm is a series of steps that connects inputs to outputs. Inputs are the starting data or conditions, and outputs are the results produced after applying the steps. These steps describe how the inputs are transformed into outputs, similar to how a recipe turns ingredients into a finished dish. By clearly defining what goes in, what comes out, and the operations in between, the same algorithm can be carried out in different programming languages or even by hand. This abstraction keeps the algorithm consistent, no matter how it is implemented. To understand what problem an algorithm solves, you must clearly identify its inputs and outputs. Inputs can be simple, like a single number such as a person's age, or more complex, like a list of exam scores. Outputs are the results the algorithm produces, such as labeling someone as a minor or adult, or calculating the highest score or an average. Everyday examples include typing information into an online form as input and receiving a confirmation message as output. By defining these inputs and outputs clearly, you can judge whether the algorithm's steps are appropriate for its intended goal. An algorithm is defined by a sequence of precise steps that describe what to do, not by the programming language used to express them. Each step should be a clear, mechanical action, such as comparing values or repeating a task. For example, when you sort a deck of cards, the unsorted deck is the input, the sorted deck is the output, and the way you sort is the algorithm. Writing this process in a language like Python does not change the algorithm itself. It simply translates the same steps into code. This shows that an algorithm exists independently of any specific implementation as long as its inputs, outputs, and actions stay the same. Python code, inputs, outputs, steps. We can use a simple temperature conversion example to demonstrate how an algorithm works, including its inputs, outputs, and main steps. This helps show that the same underlying algorithm idea can be written in different ways in Python, even though the code details may look different. The key point is to separate the abstract sequence of steps that define the algorithm from the specific Python commands used to implement it. By focusing on this distinction, you can better understand both the logic of the algorithm and the flexibility of its implementation. This line explains that you do not need to add any pip install commands because the script only uses features that come with Python itself. In other words, it relies entirely on the standard library. As a result, there are no external packages to install and no extra dependencies to manage. We define a function that converts a temperature from Fahrenheit to Celsius using the standard conversion steps. It takes the Fahrenheit value, subtracts 32 to adjust the scale, then multiplies the result by 5 and divides by 9. This calculation produces the equivalent temperature in Celsius, which the function then returns as its output. We begin with an input temperature of 68 degrees Fahrenheit and use it as the value for our conversion process. We then call the function that converts Fahrenheit to Celsius and store the Celsius result it returns. After that, we print the original Fahrenheit temperature to show what went into the algorithm. Finally, we print the converted Celsius temperature to show the output of the conversion. This example shows a simple algorithm for converting a temperature from Fahrenheit to Celsius in Python. The function takes a Fahrenheit value, subtracts 32, multiplies by 5, and divides by 9 to get the Celsius result. When run with an input of 68 degrees Fahrenheit, it produces 20 degrees Celsius and prints both values. The main purpose is to illustrate how clear, abstract algorithmic steps can be implemented in code while keeping the conversion logic separate from the specific programming details. Determinism and termination. An algorithm is more than just any method for doing a task. It must have two key properties: determinism and termination. Determinism means that given the same inputs and steps, an algorithm always produces the same result with no ambiguity. Termination means the process eventually stops and returns an answer instead of running forever. These features distinguish true algorithms from vague or endless activities and make them reliable, well-defined procedures. When an algorithm is deterministic, following the same instructions from the same starting point will always produce the same result, no matter who carries them out. A vague instruction like adding salt until it tastes good is not deterministic because different people have different tastes. In contrast, a recipe that tells you exactly how much salt to add and how long to stir is more deterministic because each step is clearly specified. In computing, this kind of precision lets us reason about algorithms abstractly without worrying about who runs them or which programming language is used. Termination in algorithms means that for any valid input, the process will eventually stop and produce an output. This requires a clear stopping condition, unlike an instruction that continues forever with no endpoint. In practice, this prevents endless loops, such as a navigation app that keeps recalculating instead of giving directions. When algorithms are both deterministic and terminating, they behave in a reliable, predictable way and can be implemented in programming languages like Python without changing their essential behavior. Python code, determinism, and termination. We want to compare deterministic loops that always terminate with loops that may never end. A deterministic loop is one where the same input always produces the same output, following a clear and predictable sequence of steps. A safe loop also has a well-defined stopping condition, so it always finishes after a finite number of steps. In contrast, a potentially endless wandering loop may lack a proper stopping rule or may depend on conditions that are never met, so it can continue running forever without producing a final result. The line with the pip install command is only a placeholder, showing where you might normally install required packages. In this particular script, it does not actually install anything. It simply serves as a reminder of where such a command would appear in a real project. We define a function that computes how many steps are needed to go from a starting distance to a target distance, given a fixed step size. It begins with 0 steps taken and the current distance set to the starting value. The function repeatedly adds 1 step's distance to the current distance and increases the step counter by 1 until the current distance reaches or passes the target. It then returns the total number of steps, and for any given inputs, this process always finishes and always gives the same result. This description explains a function that simulates a journey using a loop that could, in theory, run forever. It begins with a starting distance, then repeatedly adds 1 mile in an endless loop. Inside the loop, it checks whether the distance is more than 3 miles beyond the starting point. When that condition is met, the loop stops and the function returns the total distance traveled. This illustrates how an infinite loop can be controlled using a break condition. We define a starting distance of 0 miles, a target distance of 10 miles, and a fixed step size of 2 miles for each loop iteration. We then call a function that takes these 3 values and computes how many steps are needed to reach or go beyond the target distance from the starting point using that step size. The function's output is stored in a result variable, which represents the exact number of steps required to deterministically reach the target distance. When we call the function that calculates how many steps are needed to reach a target distance using the same starting point, target, and step size, it always returns the same result. This shows that the function is deterministic. A deterministic algorithm behaves in this consistent way, giving identical outputs whenever it receives identical inputs. This reliability and predictability are key advantages of deterministic algorithms. The code shows 2 runs of the same deterministic function. In the first run, it prints how many steps the function needs to reach the target number of miles from the starting point. It then runs the function again with the same inputs and prints the result a second time. Because both runs produce the same output, This demonstrates that the function is deterministic and that it always finishes after a certain number of steps. We use a function that simulates walking north forever, starting from 0 miles, with the distance increasing continuously. In theory, this loop has no natural stopping point, so it represents an infinite process. However, the function includes a break condition to stop the loop in practice and avoid an actual infinite loop. After the function finishes, we print the final distance reached to show what the loop would have produced if it had continued without interruption. This script compares a deterministic loop with one that could run indefinitely. The first function counts how many fixed steps it takes to reach a target distance from a starting point, and always returns the same result for the same inputs, showing predictable, deterministic behavior. For example, starting at 0 and moving toward 10 with steps of size 2 always takes 5 steps. The second function represents a loop that would never stop on its own, but is forced to break once the distance exceeds the start by 3. This highlights how loops without a clear stopping condition can potentially run forever, and why an explicit termination rule is important. Algorithms beyond code. Abstract steps versus code. An algorithm is a detailed, step-by-step plan for solving a problem that is separate from any specific programming language or code. It is like a recipe that describes what to do, not how to write it in a particular syntax. For example, choosing what to cook by checking what ingredients you have, ruling out recipes that need missing items, removing those that take too long, and then picking from the remaining options is an algorithmic process. Even without writing any code, this clear and repeatable method counts as an algorithm because others can follow the same steps to get the same result. Code is the way we express an algorithm so a computer can run it, using different languages and styles, but the core concerns are always correctness, efficiency, and readability. Correctness means the steps reliably produce the right result without errors. Efficiency is about how many operations the algorithm needs and how that work grows as the problem gets larger. Readability is about making the algorithm's steps clear and easy to follow, not just polishing the code's surface. If the underlying algorithm is complicated or poorly structured, no amount of code cleanup will make it truly understandable. Before you start coding, it is important to separate the abstract steps of your algorithm from the actual code. First, describe your approach in plain language or simple diagrams so you can check whether the steps are clear, efficient, and free of unnecessary complexity. This makes it easier to see if the logic really works and if others could follow it. Once you are confident in the algorithm itself, you can then translate it into code and focus on syntax and language details. Working this way helps you avoid assuming that code which runs correctly always reflects a well-designed underlying algorithm. Multiple ways to code. A single algorithmic idea can be coded in many different ways. For example, to check if a guest list contains a name, you might scan the list, sort it first, or rely on a built-in search feature. But all approaches still answer the same yes or no question. These options show that the core algorithm is separate from the specific coding choices. Those choices matter because they affect how efficiently the program runs, highlighting the importance of design decisions when turning ideas into working code. When implementing the same algorithm, it is not enough that a program simply works. Correctness, efficiency, and readability all matter. Two programs can solve the same problem, but one might run much faster or be far easier to understand and change. For example, a navigation app that updates routes incrementally can feel more responsive than one that recalculates everything from scratch. Clear, well-structured code makes it easier to verify behavior, adapt to new requirements, and fix rare bugs. These qualities are especially important in dynamic settings like busy cities, where systems must respond quickly and reliably. When implementing the same algorithm, designers must balance compactness and readability. A very concise solution can look clever, but may hide important assumptions and be hard to maintain. By comparing these styles, you learn to choose implementations that are not only correct, but also efficient and understandable over time. Python code, multiple ways to code. We will show the same search idea coded in several ways and compare how they differ. Using a small guest list as an example, we will look at how each version behaves in terms of correctness, efficiency, and readability. We will contrast a simple linear search that checks each guest one by one, a binary search that works on a sorted guest list, and Python's built-in membership check. Seeing these three approaches side by side will highlight their trade-offs and help clarify when each method is most appropriate. This script runs entirely with Python's built-in features, so you do not need to install any external libraries. Because it relies only on what comes with Python by default, there is no need to use package installation commands. This keeps the setup simple and avoids extra dependencies. As a result, the script is easier to use and maintain. We begin with a simple list of example names that we will use to demonstrate different search algorithms. This names list includes Alice, Bob, Charlie, Diana, Eve, Frank, and Grace. It serves as a small, manageable dataset that makes it easier to see how each search method operates in practice. By working with this fixed set of names, we can clearly compare how the algorithms locate specific items. We use the name Diana as our target, meaning it is the specific name we want to find in the guest list. This target will be checked against each entry in the list. No matter which search method we use, the goal is always to determine whether Diana appears in the guest list. This function uses a linear search to look for a target name in a list. It goes through each name one by one and checks if it matches the target. If it finds a match, it returns true to show the target is in the list. If it reaches the end without a match, it returns false, meaning the target is not present. This method is simple, but can be slow for very large lists because every element must be checked in order. Binary search works on a list that is already sorted alphabetically by keeping track of a left and right pointer that mark the current search range. While the left pointer is less than or equal to the right, we find the middle position, look up the name there, and compare it to the target. If the middle name matches the target, we report that it is found. If the middle name comes before the target alphabetically, we move the left pointer just to the right of the middle. Otherwise, we move the right pointer just to the left of the middle. This process keeps narrowing the search range until we either find the target or determine it is not in the list. To prepare for a binary search, we first create a sorted version of the list of names. Binary search only works correctly when the data is in order, so this step is essential. We use a sorting function that takes the original list and returns a new list with the names arranged alphabetically. This alphabetically ordered list is then used by the binary search to quickly and efficiently find the target name. In this example, Python's membership operator is used to check whether a given name appears in a list of names. It hides the details of how the search is performed, so the code stays clean and easy to read. The operation returns a simple true or false value, depending on whether the name is found. This concise approach relies on Python's built-in features to perform the search efficiently. We first run a linear search on the original list of names and the target name, checking each name in order until we either find the target or reach the end of the list. We then run a binary search on a sorted version of the list with the same target name. Binary search is more efficient on sorted data because it repeatedly cuts the search range in half until it finds the target or confirms that it is not in the list. Comparing these two results shows how the search method and the list order affect performance. The code first prints a message to explain what the upcoming searches will do. It tells the user that the program will look for a specific target name in a guest list using 3 different methods. This introduction sets the stage for comparing how each method works. All of the methods are trying to answer the same yes or no question, whether the target name is present in the list. We display the result of the linear search, which tells us whether the target name was found in the list. This method works by checking each name one at a time until it either finds the target or reaches the end of the list. It is easy to understand and implement, but it can be slower than other search methods when the list is large. We display the result of the binary search, which is a faster way to find an item in a sorted list. Binary search is efficient because it repeatedly cuts the search range in half, so it needs fewer comparisons to locate the target. The final output tells us whether the target name is present in the sorted guest list or not. We use Python's membership operator to check whether a given name appears in the guest list and then print the result. This provides a clear, high-level way to express the search without worrying about how the search is implemented internally. In other words, the code focuses on what we want to know, not on the specific algorithm used to find it. This code prints a message showing that different coding styles can reach the same algorithmic goal. It points out that approaches may differ in efficiency and readability, but they still solve the same underlying problem. The key idea is that there is no single correct way to write code, only different methods with their own trade-offs. This script compares 3 ways to search for a name in a list: linear search, binary search, and Python's membership operator. Linear search checks each name in order and is simple, but can be slow for large lists. Binary search is faster because it repeatedly narrows the search range, but it only works if the list is sorted. The membership operator offers a short, readable way to test if a name is present. All 3 methods correctly detect whether the name Diana is in the list, illustrating trade-offs between simplicity, efficiency, and readability. Logic-preserving refactors. When improving an algorithm, the goal is to make it faster or easier to understand without changing what it actually does. A logic-preserving refactor keeps the algorithm's input and output behavior the same while adjusting its structure or style. This can include reorganizing steps, using clearer names, or splitting complex parts into simpler pieces. Even if the internal layout looks different, the algorithm's function and correctness must remain unchanged. Logic-preserving refactors improve efficiency and readability without changing what a process actually does. For example, a logistics company can speed up truck assignment by removing redundant steps, combining related actions into one sub-procedure, or reordering checks so common failures are caught earlier. The crucial point is that after refactoring, trucks are still assigned to routes correctly under the same conditions as before. This makes the system faster, easier to maintain, and less prone to errors while keeping the original assignment rules intact. Logic-preserving refactors are essential for safely updating complex systems, such as hospital scheduling or air traffic control, where existing procedures cannot simply be replaced. Teams make small, carefully verified changes that keep the original logic intact while improving clarity and performance. Because each change is easier to test and understand, the resulting algorithms become more robust, adaptable, and accessible to new team members without introducing new errors. Python code. Logic-preserving refactors. This example shows how to refactor code while preserving its logic by using a simple temperature conversion from Celsius to Fahrenheit. We compare the original function with a refactored version and confirm that both produce identical Fahrenheit values. The focus is on improving readability and structure without changing the underlying algorithm or its results. No special libraries are required beyond the standard library. This function takes a temperature in Celsius and converts it to Fahrenheit. It does this by first scaling the Celsius value by 9 divided by 5, then adding 32 to account for the difference in the starting points of the two scales. The computed Fahrenheit temperature is stored in a variable and then returned as the function's output. We define a function that converts a temperature from Celsius to Fahrenheit in a clear and structured way. The function takes a Celsius value as input, then uses a scale factor of 9 divided by 5 to adjust for the difference in size between the 2 degree units. It also adds an offset of 32 degrees to account for the different 0 points of the Celsius and Fahrenheit scales. By multiplying the Celsius input by the scale factor and then adding the offset, the function computes and returns the corresponding Fahrenheit temperature. The function begins by printing a header that labels the columns for Celsius, the original conversion result, the refactored conversion result, and whether they match. It then loops through each Celsius temperature in the list and converts it to Fahrenheit using the original conversion function. Next, it performs the same conversion using the refactored function and compares the two results. Finally, it prints a neatly formatted line for each temperature showing both Fahrenheit values and indicating if they are the same, making it easy to verify that the refactored version behaves correctly. We create a small list of Celsius values that includes important reference points such as 0 degrees, the freezing point of water, and 100 degrees, the boiling point. We also add intermediate values like 32 and 50 degrees to give a useful range for testing. This set of sample temperatures is then used to compare the outputs of the original and refactored conversion functions and confirm that they produce the same results, even though their internal implementations differ. The code runs a function that compares the outputs of two temperature conversion functions. It uses several sample Celsius values to show that both the original and the refactored versions produce the same Fahrenheit results. This confirms that the refactoring changes only how the code is written, improving readability without changing the logic or the output. This script shows how refactoring can make code easier to read without changing what it does. It compares an original Celsius to Fahrenheit conversion function with a refactored version that uses clearer names and structure, but performs the same calculation by scaling the Celsius value and then adding 32. A helper function runs both versions on several sample temperatures and prints the results. Because both functions always produce the same Fahrenheit values, the example confirms that refactoring has preserved the original logic while improving readability. Everyday algorithms in Python, breaking down daily tasks. You can understand algorithms by thinking about a simple task like making tea. You follow a clear sequence of steps, such as boiling water before steeping the tea, and you make decisions like whether to add milk or sugar. In programming, algorithms are expressed in the same way, with ordered steps and decision points. Noticing these patterns in everyday activities helps connect familiar processes with algorithmic thinking. Preparing to go out on a rainy day can be seen as a sequence of decisions and actions, such as checking the weather, deciding whether you need an umbrella or raincoat, choosing suitable shoes, gathering your essentials, and locking the door. If you skip the weather check, you might get soaked, which shows that the order of steps and key decision points really matter. When you organize these actions into a clear sequence with conditions, you are essentially creating a precise procedure. This kind of structured procedure can then be translated into step-by-step instructions that a computer can follow. When you break down everyday tasks, you can see patterns that are important for algorithmic thinking. In activities like cooking, doing laundry, or planning a commute, you first gather what you need, then perform actions that may repeat, and finally check whether you reached your goal. Repeating steps, such as stirring until a sauce thickens, or sorting until everything is organized, and then checking the result, are not just habits, but structural parts of the process. Noticing these structures helps connect how you already think about daily tasks with how algorithms are designed in programming. From steps to pseudocode. After you break a daily task into clear steps, the next move is to turn those steps into pseudocode. Pseudocode is a structured, language-like way to describe an algorithm that is more precise than everyday language, but less strict than real code. For example, a process like making tea can be written as a simple, consistent sequence of actions using basic control structures. The goal is to show the logical flow clearly so others can understand it and later translate it into actual code if needed. Pseudocode is like giving instructions to a very literal assistant who understands structure but not nuance. You should break tasks into clear, action-focused steps and make the control flow explicit. Everyday activities, such as checking your phone until a friend replies or turning on a light if a room is too dark, can be described as repeated actions and decisions based on conditions. By expressing familiar tasks, like choosing clothes for the weather or planning a commute in this structured way, you practice the core patterns of sequence, repetition, and choice that define algorithms in computing. When turning informal steps into pseudocode, focus on clarity, completeness, and consistency. Clarity means each line should describe one clear action or decision. Completeness means including all necessary details so nothing important is left out. Consistency means using similar wording for similar actions so the steps flow smoothly. Practicing this structured approach helps you move from everyday tasks to clear code-ready representations. Coding pseudocode in Python. Once you have described a task in everyday language, the next step is to translate it into structured pseudocode that a Python program could follow. This means organizing the task using clear variable names, indentation to show structure, and explicit decisions and loops. For example, making tea can be broken into variables for amounts and times, plus actions that change those values. The goal is to keep the original logic of the task while expressing it in a way that matches how Python represents order, choice, and repetition. This approach lets you describe real-world processes systematically before worrying about exact Python syntax or error handling. When refining Python-style pseudocode, you use core control structures, such as conditionals, for making decisions, and loops for repeating actions. Everyday tasks like planning a commute can be broken into ordered steps with checks and repeated updates, which mirrors how Python handles logic. Practicing this approach with activities like scheduling or sorting emails helps you map real-world processes to Python structure. This strengthens your ability to design and implement algorithms effectively. In the final stage of writing Python-style pseudocode, you refine your structured description so it closely matches real Python while staying slightly flexible. You choose clear, meaningful names that reflect real-world elements and make sure each step only uses information that has already been defined, just as Python requires. You might, for example, first gather income, then list expenses, and then calculate savings in a logical order that can be easily turned into code. By moving from natural language to structured pseudocode and then to Python-like pseudocode, you build a mental bridge between everyday reasoning and formal programming, which makes implementing your algorithms easier. Python code, coding pseudocode in Python. In this lesson, we will practice turning simple everyday pseudocode into basic Python programs. We will use the familiar task of making tea to show how to choose clear variables and apply control structures. Through this example, we will highlight how order, choice, and repetition work together in a small, daily life algorithm. The goal is to see how informal steps become structured, executable code. The commented line indicates that you might install an extra library if needed, but it also explains that standard Python is enough to run this script. This means the code is written to work without additional dependencies, so it is easy to use with a basic Python setup. It mainly serves as a reminder to only add libraries if the script later requires features that are not included in default Python. We define a function called makeT that simulates preparing a cup of tea. It takes 3 inputs: the tea type, the amount of water in ounces, and the steeping time in minutes. These inputs make the function flexible for different tea-making situations. By putting the tea-making steps inside this function, we can easily reuse the process whenever we need it by calling the function with different values. The code starts by printing a message that signals the beginning of the tea-making process. It tells the user what type of tea is being prepared and how many ounces of water will be used. This immediate message confirms the key settings for the tea-making operation, so the user knows exactly what is happening. The code uses a simple conditional check to see if the amount of water is less than 6 ounces. This condition is used to decide whether there is enough water to make a proper cup of tea. If the water is below this threshold, the program triggers a response to handle the problem of insufficient water. In short, it ensures there is an adequate amount of water before proceeding. This part of the program checks if there is not enough water to make tea. If the water level is too low, it displays a message telling the user that the water is insufficient and that more should be added. This gives immediate feedback, so the user knows to correct the water amount before continuing with the tea-making process. In this part of the code, the else block runs when the earlier if condition is not true. Here, that means the amount of water is at least 6 ounces. When this happens, the code confirms that there is enough water to brew tea. This lets the user know the process can continue without adding more water. The code checks that there is enough water to make tea and then informs the user that the water level is sufficient. This confirmation is part of a conditional check that helps decide whether the tea-making process can continue. By verifying the water amount first, the program ensures that brewing can proceed smoothly without interruption. We begin by creating a counter called minute and setting it to 1 to track how long the steeping process has been running. This counter represents the number of minutes that have passed. Starting at 1 prepares us to enter a loop that simulates each minute of steeping. During the loop, we will increase this counter until it reaches the desired steeping time. The program uses a while loop to control the tea steeping process. It keeps running as long as the current minute is less than or equal to the total steeping time. This way, the loop tracks each minute that passes and simulates the steeping period. When the loop finishes, the tea is considered fully steeped. The code displays a message that tells the user which minute of steeping the tea is currently in. It combines the current minute with the type of tea to give clear, specific feedback. This allows the user to easily track how long the tea has been steeping and monitor the progress of the steeping process. The code increases the minute counter by 1 each time the loop runs. This step is essential because it moves the program closer to the end of the steeping time. As the counter grows, the loop's condition will eventually become false. At that point, the loop stops and the program exits after the specified steeping time is reached. The code finishes the tea-making process by printing a message that the tea is ready to drink. It clearly tells the user that the task is complete and includes the specific type of tea they prepared. This simple confirmation creates a friendly and informative end to the interaction. In this example, a make tea function is called with the arguments black, 8, and 3, meaning it prepares black tea using 8 ounces of water and a steeping time of 3 minutes. The function prints messages that guide us through the steps, checks whether there is enough water, and then simulates steeping by printing each minute until the tea is done. This shows how a function can model a simple, real-world task, with parameters that control what kind of tea is made, how much water is used, and how long it steeps. This script uses a simple function to model the process of making tea by printing out each step. It announces the start, states the tea type and water amount, and checks whether there are at least 6 ounces of water, asking for more if there is too little. It then simulates steeping by looping through each minute until the chosen steeping time is reached, printing the current minute as it goes. When the loop finishes, it announces that the tea is ready. The example shown uses black tea with 8 ounces of water and a steeping time of 3 minutes. In this lecture, you learn to define an algorithm and distinguish it from a Python implementation. Explain the importance of correctness, efficiency, and readability in algorithm design. And classify simple everyday tasks as algorithms and map them to Python-style steps. In the next lecture, Lecture C, we will go over complexity intuition. Thank you for your attention. See you all in the next lecture.